here not long ago giving the VIA lectures. And for those of us who had the pleasure of seeing those, we back for more. Great lecture, and that's great. Thanks. He will speak to us today on Pell's equation and unlikely intersection.
So thank you very much for the generous introduction and invitation, which I'm of course honored for, and it's a great pleasure to be here again. So in the talk I shall be concerned with the function field analog of the famous Pell equation. And the classical one was, of course, proposed by Fermat and goes back to antiquity and is rather universally well known in number theory. And our variant is seemingly less well known, but also appeared rather long ago, already with Abel. And the results I will describe are obtained jointly with David Masser. But before giving any result, any new result, I should like to survey a bit over this topic. So the Pell's equation, I write it in this form. And in the classical case, D is a given non-square positive integer, and the equation has to be solved in integers. And here I shall let D be a polynomial. So we replace Z with the ring, polynomial ring over some field. And we seek also solutions in polynomials. And by solution, I will always mean non-trivial solution, namely non-constant polynomial, or equivalently y is not 0. So geometrically, this problem, you see this equation defines a family of conics, of affine conics, and a solution corresponds to a section. So if you want to use this kind of language. Which assumption do we make on D? Well, first, a necessary assumption to have solution is that the degree of D is even. And I shall denote it this shape. And D also, I will assume D non-square. And usually square free. Yeah, good question. And the field K usually, for me, will be, say, Q bar, or the field of complex number. The question, as I will remark, is rather different. If we vary the field, then this makes a big difference. So the square-free assumption is, in the classical case, it is harmless. But in this case, the square factors may lead to interesting issues. But I will usually assume square-free. So, so historically, as I said, this appeared with Abel in 1826. He studied, related the equation with integration of differentials in so-called finite terms, namely elementary terms. There is, of course, this is a matter of definitions, but at that time it was understood there was a standard definition for this. And then also Chebyshev, for instance, studied the equation later in '64. So, so let us see some typical questions which may be asked. So as a first question, I would isolate for which polynomials d of t, so given the field for which polynomials d of t does a solution exist. And let us immediately call this d of t, we say they are good. So to abbreviate in the sequence. So in the classical case, when d is a non-square positive integer, a solution always exists. And so this analogy is precise only when k is a finite field. And in that case, to be positive is replaced to have a leading coefficient which is a square in the finite field. And under that necessary condition, a solution always exists. However, for over fields like this, and in general in characteristic 0, we may say, I will motivate this, I will try to give a meaning to saying that this is an exceptional situation to have a polynomial which leads to a solution. And more specifically, I shall investigate. So in the work with Masser, we focused on families. So for a single d, I shall say something, but we focused on families and one-dimensional families, actually, of polynomials d. So specifically in the talk, I shall refer mostly to this family. So where we think of lambda being, for instance, a complex parameter which varies, and we seek to understand what happens of the solvability as lambda varies. But we may, in general, think of one-dimensional families of such d. So I should remark at once that when a solution exists, if AB is a solution, then we obtain infinitely many solutions, as in the classical case, just by taking plus minus powers of a plus b square root of d. And we call this x plus y square root of d. And of course, this yields infinitely many solutions, and it is very easy to show that when a solution exists, all of them are obtained in this way, starting from some minimal solution. So another question which seems relevant to me is the effectivity. Yeah, also one may go backwards with descent. Yeah. Yeah. Oh, I see. No. I see. Oh, yes. Yes. Good. Very good. So the another issue is effectivity. So by this I mean, given d, whether effectivity, for instance, one question about concerning effectivity is whether given the polynomial d, for instance, with the rational coefficients, if we can decide whether there is a solution can we decide about the existence of a solution? And another question is, can we compute a solution if the answer to the first question is affirmative? And this I will point out that it can be done, and nowadays it may be considered a standard matter, but it was not so for quite a long time. Actually, the answer to this was found between the 50s and the 60s, I believe. So much later than the equation was considered. And I should point out immediately that, for instance, for a given degree, which is at least 4, the minimal degree of a solution is unbounded. This means that we can find polynomials D for which a solution exists, which have that degree, and for which the minimal solution has arbitrarily large degree. So this immediately points out that this effectivity question is not completely trivial, because we have not an a priori bound on the degree. And this observation, I should like to mention, that led also to a counterexample of a certain conjecture. I will not state it in detail, but formulated by model theorists. So this counterexample was due by Carsten Schmidt, Lou van der Dries, and Frank Schoutens in 2000. So this behavior led to a counterexample to us. No, it was a general conjecture on the relating in model theory of constructive algebra. And yeah, this behavior of unboundedness led to a counterexample. The conjecture looked reasonable. So let me give some examples. So let us first look at the quadratic D, and here I write down a family. And this family, so here Tn is the Chebyshev polynomial. Yeah. And un is a certain polynomial with rational coefficients. Polynomial? Ah, oh, yeah, I didn't know it. This was the name of this. So, so something familiar already appears related to this equation, and essentially, at least over an algebraically closed ground field for quadratic, all cases reduced to this example. So there are always solutions in the quadratic case, and by means of a trivial substitution, we can arrive to this example. The thing already changes in the case of quartic. And here, just to make an example, for this polynomial, say one may check there are no solutions. So already we have an example. No, I will say it later. It needs some checking. And let us illustrate another example, sextic. And I will take the example I had already written, so of this family. So there are three kind of behaviors. One may show that I will sketch a proof later if time allows. There are no identical solutions. So if we work over the algebraic closure, so if the field K is an algebraic closure of Q of lambda, then there are no solutions. So there are no identical solutions. But actually, for some special values of lambda, there are already no solutions. If the ground field, yeah. So if lambda is equal to 1, for instance, again, it may be checked that there are no solutions. And then there are other cases for other values of lambda. For instance, lambda equals 0, there is a solution. One may check this. So this behavior may happen. And this solution actually was found with continued fractions. And this leads me to the next thing that I would like to illustrate. So would like now to illustrate some issues. Oh, but there is a third one. Yeah, no. Okay. Yeah, yeah, yeah. Okay, I will move here. Excuse me? Yes, yes, Abel considered the continued fraction. So what is the continued fraction now? We start with the square root of the polynomial. And we think of it as a Laurent series, so in 1 over t. So we consider we think the behavior as t approaches to infinity. And then there is a meaning to take the integral part. The integral part becomes a polynomial. I call it a naught of t. And this is the polynomial which best approximates at infinity this function. So I have a remainder which is capital O of 1 over t. And then I can repeat the procedure of the continued fraction algorithm, writing this thing as 1 over something, which tends to infinity, and so on. And we get a continued fraction of this sort, where the AIs are polynomials. Actually, they turn out to be of degree at most d, all of them. And so what can we say? In the classical case, the continued fraction is periodic. Here, it is not always so. And Abel proved that it is periodic if and only if d is good. So if and only if there is a solution to the Pell equation. So, and so the continued fraction, of course, may be used also to obtain good approximations. And here the approximations are in the functional sense, in the power series sense, and they are classically called Padé approximations. So we find them by computing the truncations of the continued fraction. We find polynomials P and Q such that this has very high vanishing at infinity. So this, more precisely, is found to be capital O of t to the minus deg q minus 1. And if we use this approximation, we find that the degree of p square minus d q square is at most d minus 1. So this is a good attempt to find the possible solutions, but already this inequality, which can't in general be improved, indicates that if d is at least 2, this does not guarantee, of course, to find a solution to the Pell equation. I should like to mention that these Padé approximations are very useful For instance, in Diophantine approximation, for instance, they often lead to good rational approximations after specialization. So we start from a functional approximation and we get a numerical approximation, which often may lead to good Diophantine results. And in this context, for these important applications, it is relevant to know how fast the coefficients of P and Q grow compared to the degree, because this affects the specialization, the quantification of the specialization approximation. And here is a special case of a theorem brought by Bombieri and Paula Cohen. I will not state it in precision, but roughly this theorem implies that the height of P and Q grows linearly in the degree. The logarithmic height, if and only if D is good. So again, it is relevant to know whether there is or is not a solution to the Pell equation. When this condition is not satisfied, the height grows at least quadratically, and this very much affects, in the negative sense, the applications. In the case D is good, one cannot have an upper bound, a uniform upper bound for the period. This is precisely related to that behavior. Even in the classical case. Even in the classical case, yeah. So now for lack of time, I don't pause on other issues like integration, other issues in which this problem appears is the integration in elementary terms. I already mentioned, actually this was probably the starting motivation for this question by Abel. Certain differentials may be integrated in elementary terms, so-called, in the old-fashioned terminology, if and only if the Pell has a solution. And then there are extremal polynomials. This is another topic in which the equation appears. Extremal in which sense? Well, in the sense of taking the minimum of the maximum over all polynomials. So one takes, for instance, a single interval. One takes the monic polynomials of a given degree and takes, given a polynomial, one takes the maximum of the polynomial in that interval. And then one minimizes over all polynomials. In this way, one finds the Chebyshev polynomials which appear as solutions of a family of these equations. But this phenomenon generalizes. And when we consider in place of one interval, we consider several intervals. Then some case, not all the cases, in this case the thing is less precise, not all the cases, but some cases of extremal polynomials may be obtained through the Pell equation. Then there are applications also to Diophantine equations of the shape f of x equal g of y, where f and g are polynomials. This is a rather special equation, but at least I find it attractive. It expresses the common values of two different polynomials. So one may ask, when does it happen that two polynomials over a number field have an infinity of common values? And this leads to classify the curves of this shape which have a genus 1 component. And again, this may be done recently. It was done partially in a joint paper with Avanzi, and now it has been completed by Ziv and others. And there are families. There is a complete classification, and one of the families, again, involves the Pell equation and the solution. Let me mention another topic, which is so a criterion, actually, for the existence of a solution. So together with the Pell equation, I consider the hyperelliptic curve H defined by u square equal d of t. This is non-singular if d has square free, is non-singular at finite points, and it is singular at infinity, but a normalization has 2 points at infinity, which I shall denote in this shape. And so how does this relate to the Pell equation? Well, let us take a solution to the Pell equation, and let us consider the function x plus uy associated to the solution xy. So since this function times its conjugate, which I denote phi dash x minus uy, is 1, so the zeros of the function cannot have zeros at finite points. And even the conjugate cannot have zeros at finite points. So all the zeros, and the divisor is supported at infinity. But the divisor has degree 0. And so the divisor of phi must be of the shape a certain multiple of the difference of the 2 points at infinity. So now the difference of the 2 points at infinity gives an element in the Jacobian. I call it delta. This is an element in the Jacobian of the curve H. And so we see from this equation that a multiple of this element, a non-trivial multiple, if there is a solution, a non-trivial multiple of this element is the origin. So this means just that the point is torsion. So we have that delta is a torsion point on the Jacobian. And conversely, this argument may be reversed. So we have an exact condition formulated in terms of torsion points. This appears somewhat is analogous already to the classical case. You see that being torsion in the Jacobian is the Picard group. And in the classical case, the solution of the Pell equation appears in Dirichlet formula for the class number. So there is this is somewhat a relation, and this relation again is exact if we work with a finite ground field. So the Dirichlet formula is in terms of the order of torsion of this point in place of the logarithm of the fundamental unit. So, okay, so this gives an exact criterion and gives also the effectivity because it is known in principle, it is effective to decide whether a given point on a given abelian variety defined over a number field, for instance, is or is not a torsion point. This is not trivial, but it is known. So another connection which helps to motivate the word exceptional that I wrote before is provided by Biela's maps. So what is a Biela map? A Biela map is a map.
Sorry, was exceptional just not good? Is that what exceptional?
Yeah, it is exceptional that it is good. So it is an exceptional situation to have a good, yeah. So let me recall briefly. A Biela map is a rational map from a curve to the projective line, a rational map of the curve, which is unbranched out 0, 1, and infinity. And these maps are quite relevant in a number of contexts. Here, if we have a solution, so let us assume that we have a solution of a Pell equation, and we can consider the map, and let us focus for this discussion, let us suppose that the degree is given. Let's just think as small d to be fixed for this discussion. We consider the map x squared. So x squared is a polynomial map, and projectively is a rational map from P1 to P1. And it is not a abelian map in general, but almost. In which sense? Well, in the sense that almost all the ramification concentrates above 0, 1, infinity. And then there is a residual ramification which is at most d minus 1 total branching. So if I measure the branching subtracting 1, as is usually done, I have at most d minus 1 more points with total branching above those points d minus 1. Exactly. There is no bound for the degree of x, and here, if n is the degree, we have a total branching which is 4n minus d minus 1. So almost all the branching is here. Now, associated with these abelian maps and with the branching, there is a monodromy representation. So namely, the monodromy representation is a permutation representation which represents the element of pi 1 of the projective line minus the branch points. And the monodromy representation goes in the symmetric group on as many letters as the degree. So an important point is provided by Riemann existence theorem. And this theorem in particular asserts that if certain combinatorial data of purely permutation type are verified, then we may construct a map from P1 to Pn with exactly those monodromy data. And also asserts that given these data, the map is essentially unique up to an automorphism of the domain. So this means that, and this of course we must fix the points, the branch points. So this means that when we have fixed the branch points for each degree, there are at most finitely many cases of solutions, because the Pell equation gives precise combinatorial data, and so we may relate in a one-to-one way to this picture. So now we may vary the branch point, these d minus 1 points, and in this way we obtain a family for each combinatorial data. We obtain a family of dimension, an algebraic family of dimension d minus 1. So to subsum these considerations, I would state the following rough sentence, that the good d of t of given degree 2d make up to isomorphism provided by, so we consider two cases equivalent if the d's we consider D and D star equivalent if they are related by this formula. So we perform an affine transformation, and we divide to make it same leading coefficient. So up to this kind of isomorphism, the good D of given degree make up the numerable set of D minus 1 dimensional families. So this shows the sense in which I was using the word exceptional. So if we now perform these substitutions, we can always bring a given polynomial D of t in a normalized form, and suppose that it is of this shape. So there is here an m, which is the first non-vanishing coefficient, and then here there is anything, and the m is at most 2d minus 2. So this is a unique normalized form, in the sense that two of these polynomials which are equivalent, and in this sense must be equal. Then we see that we have 2d minus 2 parameters for the equivalence classes, and only d minus 1, and we have only the numerable set of families of dimension d minus 1. So forgetting the numerable, we have the double, only half of the parameters. And of course, for d greater than 1, of course, this shows that it is rare. Let me illustrate. So yeah, for d equal 1, by the way, the genus of H is 0, and we have no parameters. So up to that kind of equivalence. For d equal 2, the genus of H is 1, and so we have two parameters. For the polynomial d in normalized form. So we may assume it is, for instance, we have, for instance, this family. This family. And but the good d of t for the numerable set, this is rough, but I hope it suffices, of one-dimensional varieties, so of curves. Inside this space, which has dimension 2, we have the numerable set of curves. So this suggests that if we have a one-dimensional family of D, for instance, this one, say that we have this family, we'll let lambda vary. We have a curve inside this space, this surface, and the curve has to be intersected with infinitely many curves. So we expect infinitely many intersections, and indeed, it may be proved that we have infinitely many good d of t of this shape. So there are infinitely many values of lambda which give solutions, even if there is no identical solution. So let me illustrate one further case. Here the genus of H is 2, and we have 4 parameters for the D, and the good ones, we have again the numerable set of surfaces. And now this comes the connection with the unlikely intersection. If we take a one-dimensional family like the one I am considering, this is one-dimensional family, we vary lambda. This gives a curve in this space of dimension 4. And even if we have denumerably many surfaces, it is unlikely that the curve intersects any of these. And so we may expect finiteness. And indeed, this is what we can prove with David Masser. So the theorem, I shall state the theorem just for this special family because it is illustrative. So there are only, so this is with Masser. There are only finitely many complex mu such that T6 plus T plus mu is good. In this case, mu equals 0 gives a solution. So let me just very briefly say, so there is a similar theorem where here we can have any polynomial, for instance, of degree 6. But there are hypotheses to be verified for that for the polynomial to so. No, actually, no. We haven't the bound. Not even. So one can show that the height of these mu have to be algebraic numbers because they have to satisfy the equations for the torsion are algebraic equations. But and there is a bound for the height which I believe can be made effective. This is follows from work of Silverman in a very special case. So if we had a bound for the number, we would have a bound also for the degree, because the conjugates have the same property. And so since we have a bound for the height, it would become effective completely. Yeah, I just illustrate the two types of assumptions that have to be verified. So in general, to have this assertion, to check this assertion with some other polynomial here depending on one parameter. There are two assumptions. One is the non-existence of an identical solution. So this amounts to say that the polynomial is good over the algebraic closure of the field of function field of the rational function field. And in this case, it may be done, but the time, if time remains, I show this at the end. It is quite simple in this special case. And there is another more subtle, more difficult to check. Actually, I don't know even if it is effective to check this. The second assumption is that the Jacobian of the curve H, I call it H mu. It is associated, it is a family of Jacobians actually, is generically simple. That is, it is not isogenous to a product of elliptic curves. And this restriction is relevant, as was shown by the following example of Masser. If the d of t, the lambda of t is t to the 6 plus t squared plus lambda, means considering mu as a variable. So it may become split for special values of mu. This is allowed. We do not allow that it is split as identically as a family. Yeah, this case, for instance, is split as a family. We have two maps to the following elliptic curves. The first one defined by y squared equal t cube plus t plus lambda. And the map from H to this is rather clear. But then there is another elliptic curve, which is t to the 4th plus t squared plus lambda t. And there is a map also from this hyperelliptic curve to this curve here. It sends ty to t squared ty.
Don't these methods of Ellenberg et al. Give you?
Yeah, this.
There'll be a sufficient condition.
This is a sufficient condition, and as you mentioned, there are. It may be checked for this polynomial that the Jacobian is simple by using the way we did was by using a criterion of Stoll, which works by taking a reduction, by taking a special value, taking a reduction mod p and computing the zeta function and seeing that it does not split. But then there are families provided by work of Katz. For other families, for instance, Katz proved that under certain conditions on the polynomial f of t, this family leads to this family of curves is simple, has simple Jacobian. And then other example, as mentioned by Peter, come from work of Ellenberg, Kowalski, and others. I don't actually know, however, it would be, I don't know whether it is effective to check this condition for a given polynomial. So there are criteria which are most likely to exclude that the Jacobian is split, but if it is split, I don't know how to decide it and find the maps. So how does this connect with pink? Well, this theorem one, the connection is through the torsion condition that I have illustrated before. And actually, what one proves before to derive, there is a conjecture of pink which is very general. I won't state it. I will state this result, which I call theorem prime, which was actually formulated as a conjecture by Zhang in 1998, quite before pink. And Zhang was mainly interested in heights, but he specialized to torsion points, so zero height torsion points, and put forward the following statement at that time. And so let A be an abelian surface scheme. I use his language. Well, this is just a family of abelian surfaces over a curve, say C, defined over Q bar. And suppose A to be simple as a scheme, and let sigma.
You want fibers? You want the geometric generic fiber to be simple?
Yes. Yes. And let sigma be a section, a non-torsion section. And then the conclusion is then there are only finitely many points in the curve such that the value of the section is torsion on the fiber, of course. So the proof of this, in turn, involves a method introduced with Pisa, and it is strongly based on the counting of rational points. And this was done in a series of papers, starting with paper of Bombieri, Pisa, and especially after a suggestion of Sarnak, who actually foresaw many years before this kind of method in the context of tori. So to count the rational points and to connect this to problems concerning torsion points. And I won't say more on the proof. And so with Masser, we have carried out in a number of papers the proof of this conjecture of pink for surfaces only. Yes?
Somewhere you need a lower bound also on the
Yes. Yes. The lower bound for Galois orbits here is provided by work of Masser and Sinou David more recently, who were able to estimate the degree of field of definition of torsion points on abelian varieties in a rather uniform way. So even assuming that, even taking into account the field of definition of the abelian variety itself, which here is important because this abelian variety varies with the point, so it's very important. Yes, so in a number of papers we analyzed the conjecture of pink, which I have not stated but generalizes this thing here in the case of surfaces. And not only abelian surfaces, there are, so in the cases of all algebraic group schemes of dimension 2, and this leads to quite a number of examples of different nature. For instance, rather surprisingly, a counterexample to the conjecture of pink for this case was found by Daniel Bertrand, who found a counterexample in the case of extensions of an elliptic curve by the multiplicative group GM. And now in a paper joint also with Bertrand and Pillai, we have analyzed the situation of the pink conjecture for these kind of extensions. So, and it turns out that the Bertrand counterexample is the only one. So, but it was quite unexpected. And actually, I should like to say that this counterexample, somewhat surprisingly, this was also found by Bertrand, fits completely with another conjecture of pink. So, the counterexample, no, it doesn't lead to Pell type, but these more general algebraic groups are relevant in the context of Pell, and I shall end the lecture just by mentioning this example. So if we take the family d lambda of t to the fourth plus t plus lambda, so we are in an elliptic case of genus 1, and here there are infinitely many, say, good values of lambda, because it is of genus 1. And now, if we modify by taking now a non-square free d of t of degree 6 this time, so we just multiply this by t square, then there are only finitely many. No, I don't know.
That's strange. You're saying
Yeah.
modifying the discriminant by a square.
By a square here, it is different than in the classical case. And this is related to the conjecture of Pink in the context, in this context. It leads to find torsion values of the section on an extension of elliptic curve, of this variable elliptic curve, let us call it E lambda, by the multiplicative group. And there are other cases which relate to Pell, but the Bertrand counter example apparently does not lead to a Pell example. Okay, thank you very much.